So can everybody see the slides in their screen?
Yes.
Yep.
Yeah.
Good. So we're going to continue our discussion on the use of fatigue or concept of fatigue for designing specific components, machine components. And here we are going to see how the concepts we learned about the fatigue, generally the fatigue endurance strength, and then the fatigue failure criteria, factor of safety of estimating fatigue failure criteria, number of cycles to failure for fatigue loading. So those are the concepts that we learned in the last lecture, and we are going to use some of those concepts to see how we can design transmission shaft, or how can we actually decide on the diameter of a transmission shaft. So for most of you probably are aware about that transmission shaft are basically the one of the most commonly used component to transmit power from one component or one place to another, or basically from the power input side to the power output side, or basically from input to the load. So whatever that combination of input and output is, transmission shaft acts as a connecting medium between the source of power to the place where the power is actually consumed, or where the load is actually placed. So to decide on what should be the geometry of the shaft, or what geometry of the transmission shaft, we will use the concepts of fatigue failure and the factor of safety calculations for fatigue loading that we have seen so far, and we will actually see in this today's lecture as well. So I will go through the slides format, PowerPoint slides, and we will go through that discussion. And in case you feel like there is something, some topic or some concept that you are not able to follow through, then please let me know and I will switch to document camera. So just to recap, when we talk about fatigue or concept of fatigue, first of all, fatigue basically means reversible cyclic loading and unloading pattern. It need not be fully reversible. It is basically cyclic variation of loading and unloading pattern that a component or any machine component is. Now the cyclic loading and unloading can be fully reversible, cannot be fully reversible, can be general type, can be randomly fluctuating loads. So whatever be that variations look like, but if a component is subjected to those type of variations of load, that means the load changes with time, then what we see that the material strength is function of the number of cycles of that applied loading. And that strength is what we call as endurance strength. So we have seen that in our discussions in the last previous couple of lectures, that the endurance strength is basically a property of a material by virtue of which it undergoes failure through fatigue, fracture, or through crack propagation at a specific number of cycles when the load keeps on varying. There is a repetitive loading and unloading pattern that is applied to a specific component. So the material fails at a specific strength level, which is a function of many factors, like it is a function of surface condition, size, the amount or type of loads, whether it is an axial load or combination of torsion load or bending load. So depending on different factors and different environments on which the component is actually working or component is being subjected to, the endurance strength gets modified or gets updated accordingly. So we have to be a bit careful and considerate about what type of environments or what type of conditions a specific component is subjected to. And that is what we need to take into consideration using many factors, which we call as marine factors. So it is K subscript A, KB, KC, KD, KE, KF. All those factors have a specific relationships, empirical relationships that you can obtain from the different sources of literature, or you can also got those references from the textbook. And once you extract those specific constants, then you actually know what is the corrected endurance strength that you need to use in your design calculations. So till this point, everybody is with me, or do you think you are not following it, or do you have any questions so far? Is everybody good so far?
Yeah.
Yep.
Yeah.
Okay. So the next thing that we would like to recap is about the fatigue life estimation. So as a designer who is working with specific components that are subjected to cyclic loading and unloading pattern, the most important question is how long a component will last in service. So what basically, in other words, it is that what will be the number of cycles to failure for a given component. Now, as I said that this is one of the most powerful equation to calculate the number of cycles to fatigue. And this formula only works if your cyclic loading pattern follows a completely reversible pattern. Completely reversible pattern means it has equal amounts of positive stresses and equal amounts of negative stresses. So if you have seen this type of equal amounts of positive and negative, that means the mean of the variation is zero. Then you can use this specific formula to calculate the amount of cycles or the amount of fatigue cycles a component can last in service or can withstand when it is being subjected to specific set of environments and specific conditions. So this formula will tell you how long a specific component will last under the given cycle of reversible stresses. So you see here in this formula, you have sigma reversible, which denotes the amount of stresses in of this cycle, basically the amplitude of these stresses, and divided by constant a and raised to the exponent 1 over b, where a's and b's are functions of the material properties. If you see here, a is basically given by this expression, which is F is the fatigue strength fraction times ultimate tensile strength whole square divided by the endurance strength. And the constant B is given by this expression. So if you know the material property, or if you know which material you are working with, for example, if you're working with steel or working with aluminum or working with composite, so whatever material you are working with, you will actually get to know what will be its ultimate tensile strength, its endurance strength, and what will be its fatigue strength fraction. And based on those, you can calculate the constants A and B. And then once you know those A's and B constants, you can plug in this equation depending on the amount of stresses being applied, and you can find what will be the number of cycles to failure. So this is one of the most powerful equation that is generally used in calculation of the fatigue life. But unfortunately, this equation only works when we have the completely reversible stresses given to us. So in the most generic case, when that is not given, we will see that how that equation can be modified, and we can use the same equation to find the number of cycles to failure. But before that, there's another important slide which actually talks about, or which recaps the fatigue failure criteria that we have learned. So for example, I discussed that there are several fatigue failure criteria, just like in static failure, static loading. We have Fresca criteria, we have von Mises criteria, maximum normal stress theory. There are many theories that explain the failure of a material. Similarly, in fatigue, there are several theories that explains the failure of a material, but most commonly used fatigue criteria is called as modified Goodman criteria. And what it says that if you plot the alternating stresses, the amplitude value in the y-axis and the mean value on the x-axis, then what you have to do is you have to plot a straight line connecting the endurance strength from the y-axis to the ultimate tensile strength on the x-axis. If you connect that line is called as modified Goodman line. And that line defines the envelope of fatigue failure. So any point that lies within this line is safe. Any point that lies outside this modified Goodman line is unsafe. That means the failure will happen. And you know how to calculate the amplitude and mean. If you are given a specific cycles of stresses varying with time, then you can calculate what is the amplitude, which is the amount of deviation from the mean. So mean is basically calculated by the average of the maximum stress and the minimum stress. So maximum stress and minimum stress, take the average, you get the sigma mean. This is how you get sigma mean or mid-range component. Once you get mid-range component, then the amplitude component is simply sigma max minus sigma mean divided by 2, or it can be basically it is sigma maximum minus sigma minimum divided by 2. The amplitude is half of the total range of the variation of the stresses. So you can calculate the amplitude and mid-range component for any type of stress variation depending on the simulation of a specific component. So for example, here you are seeing a suspension arm that is being simulated at different load levels, and you can see the stresses are varying by changing the color intensity from red to green to blue. So depending on that, you actually know what is the maximum stress that this component is subject to and what is the minimum stress. once you get those two values from the simulation, you actually use this equation to find what is the mean stress and what is the amplitude. You got them, and then you need to plot that in this figure. So that's what we actually show in the next slide, where I am plotting sigma A and sigma M as point A in this chart. It is the same chart, modified Goodman line equation that tells me the envelope of the fatigue failure. And sigma A, sigma M characterizes the point A, which is basically the stress level for a specific component that I have obtained from the simulations. Does it make sense to everybody so far? If you have any questions, please let me know. I will try to explain again. Or rather, let me ask you this thing. So just look at this slide, and if you find anything in this slide is something which you do not understand, let me know and try to explain. So you have so many variables, so many equations, so many things that are basically written over here. Please look at it and see which of the terms, expressions, variables you are not understanding. If you find something new and MS, let me know and I will try to explain what that means.
Can you go back to the other slide, Professor? I think some of this stuff from the other slide. Yeah. So.
Okay.
What's SE again?
SE. So SE is basically called the endurance strength. That's what we were discussing. The first slide I was talking about, that it is the strength of a material which depends on the number of cycles of loading and unloading pattern a component is subjected to. So depending on the number of cycles of loading and unloading pattern, the strength value keeps on changing. And that basically is reflected in this property, which we call as endurance strength.
Okay, thank you.
Yeah, welcome. Yeah, please look at the slides. Look at this slide and let me go to the next. And look at this slide and let me know if you have any difficulty in understanding any of the parameters that are mentioned in this. And let me know as well if everything makes sense to you. If you guys are completely comfortable with whatever has been mentioned in here, let me know as well, please.
Could you go over what the modified Goodman line is again?
Sure. So modified Goodman line is basically saying that if I plot this point A, do you understand what is point A here?
Yes.
Oh, but before we discuss anything, can you identify yourself so that I know your name and then?
James.
James. So you know how point A is plotted and which basically is coming from the simulation values, right?
Right.
Okay, now if point A is lying beneath this line, that is on the left side of this line towards the origin, then I know that my material is safe. It is not going to fail under fatigue loading. But if this point A is lying somewhere near point C, that
okay.
my failure will happen. Fatigue failure will happen. So what this modified Goodman line is saying that it is the boundary between the failure and not non-failure.
Okay, gotcha.
Yeah. And this load line basically tells you that how much is the factor of safety I have for my point A. So how much point A can be increased, how much loads can be increased for point A such that it can reach till point B where the failure will take place. And that will define my factor of safety. So I can measure this length of this line, which we call as load line. And I believe everybody understands what load line means. So load line, to reiterate, it is basically the line which is representing the increment of the stresses in the same proportion. So I am basically using this line. Basically, I means that I am increasing my amplitude and I am increasing my mid-range value in the same proportion, and I can keep on increasing. That means I can keep on increasing and moving in the same line till I move and reach this point B. The moment I reach this point B, that means I am at the boundary of my failure. I cannot go any further without the failure will happen, without the failure of the material happening. So that means I can wait, or I can increase my load levels till point B along this line. Does it make sense?
Yes.
Any questions from anybody else? So I am assuming that you guys fully understand what has been mentioned or any specific constants and parameters that are used here. So just to make sure that we understand about what is Langer line or yield line, it is basically also a failure envelope, but it is a failure envelope due to material yielding. Yielding means that material has plastically deformed. So as you can see that this line is also a failure envelope, but it represents the envelope due to material yielding. And modified Goodman line is a failure envelope that represents a failure of a material under fatigue loading, under fatigue fracture, where the crack propagates and becomes critically becomes that much long, which is a critical length, and from there it breaks, it snaps. The structure or the components just snaps because of the critical length of the crack formation. Now, as you can see, there are these two envelopes. They are at different slopes, and they are intersecting at that point. From here onwards, you will see that the modified Goodman line is extending beyond the envelope of yielding. So that means if somehow my load line, which was like this, if it would have been lying like this, then that means my failure will first take place under material yielding before the fatigue failure. So material will yield first before the fracture takes place. So this two envelopes actually tells me which of the two failure will happen, whether the material will fail under crack formation or whether the material will plastically deform. So for example, I know for ductile materials like steel, aluminum, and any other copper or any other ductile materials, the failure of a material is defined by yielding or by plastic deformation. So in those scenarios or in those type of applications of ductile materials, ductility is there, you may have fracture as well, the cracks formation as well, and the material will fail under fracture, and that is because of the fatigue, as you can see here. So the ductile material can fail by crack formation as well as under plastic deformation. So if the load line varies like this, then the crack formation will occurs first before the yielding takes place. But if the load line is inclined such that it is lying very, very close to the horizontal axis, then my line will first hit the yield line first, and then it will go to hit the modified Goodman line. That means my failure will take place by yielding. So these two failure envelopes will be competing with each other, and whichever is lying low will basically defines the failure envelope. So failure envelope will basically be like this, and then at this point it will change the direction and will become like this. Are you guys able to follow what I'm doing here?
Yes.
Yeah, pretty much it switches because then the yield line comes before the
Yes.
Goodman line, right?
Yes, exactly.
Okay.
Exactly.
And you said the yield line, so the Goodman line means that it would crack or fail, and the yield line means what? That it will
Plastically deform, plastic deformation will take place.
okay, kind of like it would bend past its return point, or I forgot what the
Yes. Yeah, it will basically deform and it will basically go under permanent deformation. Permanent strain will set in.
That's what I was looking for. Permanent deformation. Okay. Yeah.
Yeah.
Okay. Makes sense.
So permanent deformation will set in, and in modified Goodman line case, it will be fracture. The crack formation will take place and the material will fracture. It will just cracks will appear. Does it make sense to everybody so far?
Yeah. But basically, Professor, just a general question. We would have to pretty much like, would we have to make this tape or plot for any material we're using, or is there like a already like a general chart that we use?
No, we have to use this construction for every single case we are analyzing. So whether you are analyzing a given cantilever beam, which is undergoing repetitive loading and unloading, or whether it is a suspension arm, or whether it is a transmission shaft. So for every specific load and situation and given application, you are going to construct this line, this chart, to see whether the fracture will take place or whether yielding will take place, what is the factor of safety, and so on and so forth.
Okay.
Yeah. Cool. Any other questions from the class?
When it comes to the homework, do you want us to draw these to scale, or is it okay if we draw the lines and label off intersections and points?
If you are asked to calculate the factor of safety, then yes, you have to draw it using scale. But at the same time, you don't need to construct graphical like this. You can just simply use this equation and you can calculate what your factor of safety is. N is your factor of safety in this equation. And this equation is nothing but the equation of the straight line. It is x over x intercept plus y over y intercept, and n basically represents the factor of safety. So this is just an equation of a straight line, and that represents the equation of modified Goodman line. So if you know what is sigma A is, the amplitude of the stresses, if you know what the mean of the stresses is, and you know what the endurance strength and ultimate tensile strengths are, you can calculate what the factor of safety is using this equation.
Thank you.
Yeah, welcome. Okay, are you guys okay so far?
Yes.
Cool. And the last one is last thing that you basically probably know now, that to use that equation about the number of cycles to failure, what you need to do is you have to construct a straight line connecting ultimate tensile strength on the x-axis to the point A, the value of the stresses that are being applied. And wherever this straight line intersects the y-axis, that will represent the equivalent reversible stresses that you can use in this formula to calculate the number of cycles to failure. So to use that equation about number of cycles to failure, you have to find the equivalent reversible stress, because in general case, you are not getting a completely reversible stress. So you have to find an equivalent reversible stress to use in this equation. I hope you understand what I'm trying to say here about this equivalent reversible stress. If you see at this point, the mean component is 0. So this point, basically any point on this y-axis corresponds to the mean 0. Sigma m is 0, any point on this y-axis. And that is what we need in this formula or in this expression to calculate the number of cycles to failure. So that is why we have tried to find the equivalent reversible stresses by connecting this straight line and seeing wherever they intersect. Okay. So now we actually switch the discussion to more qualitative discussions about the design of transmission shaft. So far what we have seen is how fatigue of our fatigue loading to a material causes failure, what type of strength degradation takes place. So the specific strength parameter that we need to use in fatigue is called as endurance strength. Then we have seen how to use modified Goodman line and how to calculate the factor of safety, and also how to calculate the number of cycles to failure. We will use those concepts to decide the geometry of a specific component, and that specific component we are right now looking at is transmission shaft design. So how transmission shaft is basically designed, or is how the diameter of the specific shaft and what type of materials are generally selected. So these are some of the considerations we will first go through, and then we'll see how to use those calculations to calculate the transmission shaft diameter for a given application and given load situation. So when we talk about design of a specific component, and these considerations will remain the same for any component, machine component, whether it is bearings, whether it is gears, pulleys, belt drives, whether it is chains, or anything, any other component that we will actually look in 472 specifically, whether it's suspension, whether it is springs. You will actually see that the design of those components, or any machine component, follows the consideration about the choice of material, the geometry of it, what type of diameter, what type of geometry it must have or it must possess. Then the discussion is, or basically consideration is about the stress of the allowable stress in that material, the strength calculations. And when we talk about stress and strength calculations, we have to look for both the static loading, allowable static load and allowable fatigue load. So we have to basically take into consideration the failure of a material under static loading and the failure of a material under fatigue loading. So we have to basically consider both of the failure theories we have learned so far for the application of static loads and fatigue loads. So those are the stress and strength considerations we need to provide, or we need to consider for a given component. Then the next point that comes and the consideration is the deflection of the material or deflection of the component and the rigidity of it. So rigidity defines how much stiff a material is, how much deflection or how little deflection it will have under the given applied loads. So when we talk about deflections, now the deflections will depend on what type of loads are coming. If it is a bending load, then we have to calculate the bending deflections. If we are talking about torsional load, then we have to compute torsional deflection or twisting of the, or the rotation component or the twisting of the material. If we are talking about the shear loads, then we have to talk about shear deflection and slope at bearing locations. So those are some of the considerations we need to provide for any component. If it is the transmission shaft, so we will have those considerations tuned towards the transmission shaft. If it is another component, then we have to tune our considerations for that component as well. And then since this is this component transmission shaft specifically is under dynamic load, so we have to also be considerate about the vibrations due to natural frequency. So what type of resonance that can take place? What is the critical speed by that we have to be careful about, such that the transmission shaft does not undergo resonances. So those are some of the things that we will be considering in the designing of the transmission shafts. So first, let's talk about material. So material selection is the first step in any design process. And again, when I say that the first step, it does not mean that you have to have a complete picture, or you have to final choice of the material is done at this point. So design is always iterative in nature. You choose a material and then you apply the stress and strength calculations, you apply the loads, you find out the factor of safety. And if you feel like those factor of safeties are not sufficient, the material is not having proper strength, then you have to go back and change the material. And then strength and stress calculations are not the only parameters for material selection, but the other criteria for material selection is the weight aspects, the manufacturing aspects, how easy it is to manufacture a component with that material, then the price, availability, and then also the stiffness of it, how stiff the material is. So if you feel that it is deflecting a lot, that means it does not have the proper stiffness or rigidity that you need to consider. So a lot of the factors go into play, or in deciding on the choice of material. And again, when you decide on a choice of material at the first instance, that does not mean that you cannot change that. You can always go back to your design calculation and change the material. And that is what we call as iterative design procedure. Or basically, as I said, that design is always iterative in nature. You have to go back and forth and make iterations. So here also, we start our design by selecting a specific material. Now, commonly the material that we select for transmission shaft is generally steel or low carbon steel that are typically used in all industrial applications. Low carbon steel or cold drawn or hot rolled steel, both are equally used. And the typical candidates is AISI. It is a specific grade of steel, 1020 and 1050 steels. So those are the choice of materials that are selected as a first iteration or design iteration for your calculations, or for sizing, or for finding the factor of safety of the transmission shaft. The part is that if you do not select a material, then you can no longer do any calculations, because for any calculations, you need to know what is ultimate tensile strength, what is the endurance strength, what is the yield strength, And all these parameters depend on a specific material. So if you do not select a specific material at the very first step, you cannot go do any other calculation. So that is the reason you have to select a specific material, and that selection is based on what is commonly used in the field, in real life applications. In many other applications, what are the common choice of material? So we start with that choice, and then we keep on doing the calculations. And if we see our factor of safety for our application is very, very high, then we will go back our first step and say, no, I don't want to use a material. I can change the material A to material B and redo the calculations. Does this make sense to you guys?
Yes.
Yeah.
Yes.
Okay, any questions so far what I have been trying to explain?
Not yet.
Okay, so as I said, the steels are the most common choice of materials for transmission shaft. Again, there are many other considerations like surface hardening is required or not. So surface hardening is necessary if you are mounting bearings on the transmission shaft, or if there is some component or being mounted like pulleys, sprockets, gears. If they are mounting any specific component on the shaft, then that surface should act as a bearing surface, and that should be surface hardened. Surface hardened means that it should be resistant to wear and tear during the relative motion of the components on that surface. Does it make sense? Yeah.
Yes.
Yes.
Now, the reason it becomes important to know those specific manufacturing processes that are required is that any process, any type of manufacturing process that you are going to use is going to affect the endurance strength of a material. If you remember from the very first slide, when I was talking about the endurance strength, which is basically the strength of a material when it is a function of the applied fluctuating load as a function of cycles, that endurance strength depends on what type of manufacturing processes are being used. So if you are using a surface hardening, you are causing the material to have a lower endurance strength. So basically, depending on what type of manufacturing processes are being used, the correction factors like Ka, Kb, Kc, if you remember those correction factors, they keep on changing. So you have to keep track of what are the manufacturing processes are used, what type of environment, what type of operating temperatures are being used. So all these factors make a significant, a pivotal role in selecting the design parameters or design values. So that is why you have to be careful about what are the processes that have been used and what are the environments and operating temperatures. So surface hardening, again, as I said, it is required only on those portion of the surface, on portion of the shaft. Generally, transmission shaft is generally longer, and you need surface hardening only on those portion of the shaft where the mounting of the bearings and gears and sprockets and pulleys will take place. You don't need to surface harden the entire length of the shaft, because that is basically you are unnecessarily doing that process, and you are incurring the cost without requiring the shaft to have the surface hardened throughout its length. Okay, so generally when the shaft size is smaller, it is less than 3 inches, the preferred production is cold drawn steel. Generally it can be manufactured using drawing process, where you actually have a shaft drawn from the bars, and you can have a cold drawn operation, a cold drawing process. But if you have a larger size shaft, then the material is the shaft material, or the material to be drawn is very significant. Then you need to go for hot rolling process or hot rolled steel. That's what we call as HR steel, is hot rolled steel. That is generally used, that manufacturing process is generally used for larger size or larger diameter shaft. And again, it should be machined. If it is a hot rolled steel, it should be machined all over. Then as if it is a low production quantity, then lathe machining is typical. And for high production quantity, forming or casting is generally typical. And as you can see that there are many factors, other factors that also go in the material selection, but these are most of the significant ones that we actually use for transmission shaft. Any questions so far, guys?
No.
So we've now come back to the transmission shaft diameter calculation. So once we have selected a material, then we know what are the endurance strength and ultimate tensile strength and other parameters we need to consider. So the next question is, what should be the diameter of the shaft for a given application? So how do I know whether I need a 2-inch diameter or a 1.5-inch diameter, or 3-inch diameter, or 4-inch diameter? So how do we decide on the diameter of the shaft? So in this process of estimating diameter, we need to do the calculations that we have just seen. It will be the same calculations, similar calculations rather. So first we know that transmission shaft is being subjected to cyclic loading. Transmission shaft, as we know, it is not subjected to a static loading. So it is also subjected to cyclic loading or fatigue loading, because the transmission shaft keeps on rotating, and because it rotates and it is also withstanding some loads, bending loads. So we know that this is going to undergo fatigue loading, and we know what should be the amplitude and the mid-range component. We can calculate that. And we talk about the transmission shaft. So generally it has a bending moment and a torque, and each of the bending moment and torque will have its amplitude component and the mean component. So if you see here, sigma A is the bending stress, Kf is basically the stress concentration factor. So this is M times Y divided by I. It is C, basically represents the distance from the neutral axis. So it is just the same formula we use to calculate the bending stresses. And M subscript A denotes the amplitude. M subscript small m denotes the mean or mid-range component. So what it is saying that if your bending moment fluctuates, then for that fluctuation, you know what is the amplitude of the bending moment and what is the mid-range component of the bending moment. And that will give me the bending stresses, the amplitude of the bending stresses, and the mid-range component of the bending stresses. Similarly, for twisting, I know I can calculate the shear stresses due to twisting movement or torque. Now, again, we have a subscript A and M that represents the amplitude component and the mid-range component. So for circular cross-section, this is further simplified using the I, the moment of inertia is given a pi times d raised to 4 divided by 64, and C is d by 2, so it becomes 32 m divided by pi d cube. And the shear stress becomes 16 times torque divided by pi d cube. Everything else remains the same. So if you follow this, the next step would be to figure out what would be the stress concentration factor. But before I actually move to this slide, let me ask you, is everybody following it so far, or everybody is with me, or do you have any questions, or you have any confusion about understanding what is happening here?
Could you explain what MA and MM is in the equation 7.1?
Yeah, MA is basically if your bending moment keeps on changing. So imagine that the bending moment also varies like this. So when a bending moment varies like this, then what will be MA? MA will be this value. And what is MM will be this value.
Oh, okay. Thank you.
Yeah, welcome. So instead of stress like this, I have bending moment like this. If I have bending moment like this, that means I will have MA and MM, and that will give me sigma A bending stress, the amplitude of the bending stress, and the mean component of the bending stress. Okay. Yeah, please, I will ask all the class to please have a look at this slide and let me know if you are not comfortable with any single variable or any specific equation. I'll try to explain you what it means.
Sorry, and Professor, for the values of these constants, we'd get them from the properties of the material we're using, correct?
Which one?
So let's say like KF.
KF, okay, yes. So KF, I will explain in a second what KF means. KF is a stress concentration factor for fatigue loading, not for the general stress concentration factor, but fatigue loading. So I will explain to you just in a couple of slides,
Perfect.
What KF are.
Okay, thank you.
Yeah, welcome. Yeah, please look at, I will ask all the students here, please have a look at this slide and let me know if any variable, any expression, any equation does not make sense to you, I will try to explain. So everybody is good so far?
Yeah.
Okay, assuming that everybody follows the discussion so far. So I'm going to discuss next what this KF on KFS basically means, and how do we get to know what these constants are, because these are called the stress concentration factors. We have not been using these in our calculation so far, but what we'll see that in fatigue especially, that these factors play a pivotal role or are becoming significant, because the stress concentration will change the factor of safety as well. So let's discuss what stress concentration factor. So here I'm showing you a specific situation, a plate, simple plate, rectangular plate with circular hole at the middle. And you are basically applying uniaxial stresses in one direction. So this is a simple square plate, or maybe a rectangular plate, you can say. And you have these applied stresses in one direction, and you have a hole at the center. So what you see that these lines are dotted lines. These lines represents the flow of stresses in the material. So as you will see, if I'm away from this hole, the flow of these stresses, the dotted lines are straight. So basically it means the stresses are in the same direction as my applied stress, the uniaxial direction. But as I come nearer to my hole location, you will see that the flow line, dashed lines will change the contour. And that is basically mean the stresses are changing the direction, because the stress needs to go from, you cannot just pass through the hole, it has to go within the material. So within the material, the flow lines will change and will conform to the geometry of the discontinuity here. So hole here represents a discontinuity in a material. So because of this discontinuity in the material, the flow lines of the stresses gets distorted. It basically conforms to the geometry of this discontinuity. And because of this discontinuity or this non-uniformity of the flow lines, what you will see that the value of the stresses at the edge of the hole becomes larger than the value of the stresses at the outside or exterior location of the hole. So basically away from the hole, the stresses are just equals to the applied stresses, but near the hole location, because the flow lines gets distorted, my stress value becomes increased. And that is what we call stress concentration. So the stresses are basically concentrated, and that concentration of stresses is represented by the ratio of sigma max, the maximum discontinuity that happens, to the average stress the nominal stress that would occur away from the discontinuity. So that is what we call a stress concentration factor, KT, K subscript T, and KT is basically representing the stress concentration factor due to normal stresses, and K subscript TS represents the stress concentration factor due to shear stresses. Now here on the right hand side of the slide, or right hand picture here, shows a simple simulation of the similar rectangular piece where you are applying the axial loads or stresses, and there is a hole at the center, and you can see that you have red colored intensity of the stresses showing it is maximum at this point, and then it becomes average away from the center of the hole, and it is almost equals to the value which is generally in this situation the stress concentration factor, the maximum stress concentration factor is 3. And if you can look at the label here, I mean, it's very small, I know, but if you can zoom in and look at it, you will see that it is much closer to the value 3 here. It is around 2.774, I believe, 774E0. So 2.774. So depending on the mesh, the size of the mesh, you can capture it, or you can make it, basically you can capture the stress concentration factor, which will go much closer to the value of 3, which is the maximum stress concentration factor for a plate with a circular hole. Does it make sense, guys?
Yeah, it does. But sorry, Professor, why do you want it to be a factor of 3 or closer to a value of 3?
Oh, okay. So I'm just saying that for a given structure, which is a rectangular plate with a circular hole, the maximum stress concentration factor is 3. It is not beyond 3. So depending on the on the geometry of the plate or geometry of the base structure and geometry of the discontinuity, you have different stress concentration factor. So for a given rectangular plate with a circular hole, the stress concentration factor is generally 3. Maximum concentration factor is 3.
Okay. Oh, okay. It's just like a known value. So like if the hole was a triangle, then the value would
It
be
is different. Yeah.
blah, blah,
If
blah.
it is
Okay.
hole is elliptical, then the stress concentration factor will be different. If it is a notch, it will be different. So for different size discontinuity, you have different stress concentration factor. But
Okay.
for circular hole, the maximum stress concentration factor is 3.
Okay, perfect. Thank you.
Yeah, welcome. So these are the stress concentration factors we call as theoretical stress concentration factor, and it depends on the geometry of the discontinuity. If it is circular hole, it will be 3. Elliptical hole, it will have different relationship. It's 1 plus 2 times A over B. A is your semi major axis, and sorry, A is a minor semi minor axis and B is semi major axis. So you will get those formula from different charts. Similarly, if you have a notch, it will have different formula. So you can see that depending on the geometry of the discontinuity, you will have different stress concentration factors. So in case of transmission shaft, we will have similar instances or similar situations where my stresses will be concentrated. So if you look at a typical transmission shaft, you will find that transmission shafts are always in a stepped construction. Stepped construction means it will have a bigger diameter and then it will have a smaller diameter. And it will have bigger diameter again and then smaller diameter. So it is basically falls, it actually goes through a stepped construction. So it has different diameters and different lengths. So when the diameter is changing from big diameter to small diameter, you basically see the change in geometry is taking place. And if you can see the lines here, dotted lines, I'm not sure if it is visible or not, but if you see these lines represents the stress flow lines. And again, you see the flow lines keep on changing and getting concentrated at this region. And this is why the stress concentration is happening at the shoulder or location of the shoulder radius, which is basically the interface between the bigger diameter and the minimum or the smaller diameter. And to reduce that stress concentration, there are various manufacturing steps generally are used. One is that you have a large radius undercut. So basically it is undercut into the shoulder. You can have that undercut to have a reduce the stress concentration factor, or to basically have a less distortion of these stress flow lines. Or you can have these type of grooves you can cut in the shoulder, larger shoulder, or you can have a relief groove on the smaller diameter. So these are some of the manufacturing processes or techniques that are available to reduce the stress concentration in transmission shaft. Does it make sense, guys?
Yeah, it does.
Yes.
Great. Okay, so when again coming back to the discussion we are having about stress concentration factor, you see here that this chart represents the stress concentration factor as a function of the diameter of this hole and the width of this plate. And you will see that the maximum stress concentration factor is 3, and it keeps on decreasing depending on what is the diameter to width ratio of the plate is. And this is purely a function of geometry. It is just that if you have different diameter of the hole or if you have different width of the plate, you will have different stress concentration factor values. Similarly, if you have a transmission shaft, you have a bigger diameter and a smaller diameter, and the radius of the fillet radius is given here. Then based on that radius of the fillet, you will actually find the stress concentration factor changing its values like this. So there are different charts that are available to let you know what those stress concentration factors would be. And these are purely a function of geometry. Now, when we talk about fatigue factor of safety, we have to use those KT values and use this relationship to find KF and KFS. These are the values we were using in our calculations. If you remember a couple of slides back, we were using KF and KFS. And that basically means it is a fatigue factor or fatigue stress concentration factor. And it depends on the KT value, the theoretical stress concentration factor, and Q. Q is the notch sensitivity. Again, you have charts for different materials, how the notch sensitivity changes as a function of notch radius. So this is a notch sensitivity and notch radius. So if you know the notch radius, you can find the notch sensitivity for different materials. If your material is 200 kpsi ultimate tensile strength, the notch sensitivity will vary like this. if a material has 60 kpsi, kilopounds per square inch ultimate tensile strength, the knot sensitivity will vary using this chart. So you can find different charts to find your Q or the knot sensitivity, and from there onwards you can calculate what your stress concentration factor would be for fatigue loading, Kf and Kfs. Let me know if it makes sense to you guys, or if anything here does not make sense, please let me know. Try to explain again. So are you guys good so far?
Yeah.
Yes.
So I'm assuming that everybody is following it. I'm getting responses from only a couple of students, but I'm assuming that everybody is following it. If you have any difficulty again, please let me know and I'll try to explain again. Okay, so coming back to our transmission shaft diameter calculations, as I was showing you in a couple of slides back, that you can calculate your sigma A and sigma M. And here, this is just a von Mises stress formula. So you just plug in the values of sigma A and tau A using the von Mises stress formula. And this is thereafter you use the modified Goodman line equation to find what should be the diameter of the shaft. So in all these expressions, the unknown is your diameter, transmission shaft diameter. So diameter is not known to you. So everything else is known. You know what is the factor of safety you're going to apply, what is the endurance strength you're going to apply, what is the ultimate tensile strength, because you already have selected a material. You already know what is the bending moments that are being applied, what is the twisting moments that is being applied. So everything is known in these equations except the diameter of the shaft. So there are two methodologies to calculate the diameter of the shaft. One method is that you use these equations and you solve them for your diameter d, and it becomes this expression, this long expression here. This long expression basically means that if you plug in the values of your MA, that is the amplitude of the bending moment, amplitude of the twisting moment TA, MM is the mid-range component, mean of the bending moment and mean of the twisting moment, and KFS is the stress concentration factor for fatigue under shear loading. KF is the stress concentration factor for fatigue under normal stresses. So if you plug in all those numbers, N is your design factor of safety. If you plug in all these numbers, you can find what should be the minimum diameter that you need for the given application. So this is one method or one way of calculations. Another method of calculation is that you begin with an iteration, So you begin with a specific assumed diameter. You assume the diameter is, let's say, 0.5 inches. So by that assumption, you can calculate sigma A prime, sigma M prime, and you find out what will be the factor of safety. If you see the factor of safety is very high, that means you have the margin to reduce the diameter. If you see the factor of safety is low, then you can increase the diameter in your next iterations of calculations. So in the next iteration, you change from 0.5 inches to 2 inches, and you keep on doing the same calculations and see what will the factor of safety is. So this way you can do the iterative calculation. So there are two methods. One is you directly solve this long expression for diameter, or you keep on assuming the diameter and do the iterations for finding what is the factor of safety you are getting. Does it make sense, guys? Or I completely lost you here?
It makes
Still
sense.
with you.
Okay. Anybody who is not feeling comfortable in this expressions or explanation, please let me know. I'll try to explain it. Okay, assuming that everybody is following it. Now, I'm making this life easier for you guys, that now the transmission shaft, generally the M subscript M is 0. That is the mean of the bending moment is 0. And the amplitude of the torque twisting moment is 0. So what is remaining in the long expression is only these two terms. So diameter can be calculated using this simple expression, where 16 is a constant, N is a factor of safety, pi, SC is your endurance strength, 2 times Kf is the fatigue stress concentration factor, Ma is the amplitude of the bending moment, SUT is ultimate tensile strength, root 3 times KFS is the fatigue concentration stress concentration factor for shear loading, and T subscript M basically means the mid-range component of the applied twisting moment. So if you have a transmission shaft that is subjected to bending moment and torque, then those bending moment will basically means it is MA, because M subscript M is 0, and the torque is given by Tm because T subscript A is 0. What it basically means that the twisting moment is a steady state torque, and bending moment is basically completely reversible bending moment that is being applied to a rotating shaft with constant bending moment and torsion. So these are the simplifications you can make, and you will get the long expression for diameter that you see in the top. It actually becomes this simple expression like this here.
And in relation to that, would that be an example of a vehicle going at a constant speed on a highway per se?
Constant speed on a highway. Let me see. So yeah, you may say that, because now you are saying that a steady state torque is applied. That means the torque is not varying and the bending moment does not have a mid-range component. So yeah, that's what you are basically saying is perfect example of this specific expression of calculated diameter. Yes.
Okay. Perfect. Thank you.
Yep, that's a good example basically to explain the use of this equation. Any questions from anybody? Okay, so if not, then we will actually basically have seen two of the important considerations. One is material choice and another one is the transmission shaft. So if I go back a bit again, if you find that the diameter is basically for a given factor of safety and given choice of material, diameter is coming out to be, let's say, 20 inches. And you know that you cannot accommodate 20 inches diameter of the shaft in your gearbox or in your packaging constraints of the vehicle, and you only have the space for, let's say, 10 inches diameter. So that means you need to reduce the diameter from 20 inches to 10 inches. Then what can you do is you basically go back to your choice of material and you can look for different materials such that your endurance strength and ultimate tensile strengths are different or higher, and then that way you can reduce the diameter of the shaft accordingly. So depending on choice of material, the diameter will get reduced or increased or changed, and depending on your packaging constraints, you can select a specific material that will give you a diameter that matches the space requirement, a space constraint of your packaging, packaging of a vehicle or any other machinery that you are working on. Make sense, guys?
Yes.
Yes.
Great. So having done that, or having seen the choice of material and the diameter that is required for a given application, now this is basically some guidelines or considerations for layout, that how it should be laid and how the components, different components are mounted on the shaft. So generally the layout to accommodate shaft elements, basically the gears, bearings, pulleys that are actually mounted on the shaft, needs to be decided at the very early stage, because that will define how the bending moment has to be calculated, how the twisting moment has to be calculated. So some of the information about the placement of the gears or the bearings needs to be known beforehand. And as I have mentioned, that if you see this is a transmission shaft for a specific gearbox, and you see it is basically a stepped construction. You have one diameter, then bigger diameter, then another bigger diameter, another step, another and step. I believe that is not a step, it is a hub. And the step is only this much. This transmission shaft goes like this. And then you have probably another step and it will go like this. So this is basically a step geometry. The transmission shaft, if you see in any construction, in any application, is always follow the stepped geometry. And the reason that it follows step geometry is because you have different components, like here the bearing actually gets located axially because of the step in the construction. So if you have a step in diameter, that bearings, the gears, they actually gets a means to locate in the axial direction. So that is one reason that you have a steps in the transmission shaft. Another reason that the steps are important is that axial load is being transferred or transmitted by the steps. So if you have an axial load coming in the shaft, so somebody is pulling the shaft or pushing the shaft here. So if there is some axial load coming, so those axial loads are getting transmitted by the steps in the shaft. So that steps will help to transmit the axial load from bearing to the housing and so on. So the axial loads, the pulling load or the forces gets transmitted to the housing or other member of the structural component using this step geometrical or step construction. Does it make sense, guys, so far?
Yes.
Yes.
Any questions from anybody?
Professor, is that picture supposed to be a transmission or like a differential or?
So this is basically a differential, not a transmission, because here you only see one gear here and the other gears are basically arranged in a cross pattern, basically in the 90-degree pattern, bevel gears. So it is not exactly a gearbox because you only have one gear mounted over.
Okay.
Okay, so some of the other considerations is that generally the good layout is that you have transmission shaft laid out such that the bearings are located at the extreme ends and the gears are located between those two bearings. Generally, you don't want more than two bearing supports for transmission shaft, because if you have more than two bearing supports, then you will have static redundancy. It will become difficult to calculate the reaction forces. So the rule of the thumb is you use only two bearings. Generally, you prefer to use two bearings unless the length of the shaft is that long that you need to use third bearing as well. So as much as possible, ensure that the bearings are at the two opposite ends and all the other components, the power transmitting components or transmission components, are placed in the middle or at the center, between the two bearings. If it is not possible, generally when you have pulleys and sprockets, then those are basically becomes a cantilever arrangement. That means you have bearings here, this is a fan and this is a pulley or a sprocket here, and this is basically cantilever arrangement. But you have to make sure that the overhanging portion of the shaft should be as little as possible, because otherwise there will be excessive bending deflection that will take place. So make sure that the length of the shaft overall is smaller and also the overhanging portion is also smaller. So those are some of the other design considerations that you probably have to consider, and these considerations will come into picture when you actually work with the specific choice of transmission shaft for a given application. So from application to application, those guidelines keep on have different guidelines, and different guidelines means different guidelines for different applications. So for specific application, you need to consider what specific guidelines are there for the layout of different components on the shaft. Okay, and another one, as I was mentioning here, yeah, axial loads that are going to be transmitted must be carried through only one bearing. It is a good practice that only one bearing should carry the axial load. And due to temperature changes, it may happen that if you see that this is a transmission shaft here, this is a blade as a mowing spindle, a machine spindle. So you have a blade mounted over here, you have a shaft, and then you have bearings located at these two positions. And if you see these two bearings, this bearing is completely encased. It cannot move in the left or in the right. But this bearing is free to move on the left side, but it is not free to move on the right side. And the reason it is basically have this axial movement or this flexibility to move in the left direction is because if for some reason the transmission shaft gets hot or gets, high temperature, then it will elongate. And if my bearings are not allowing it to elongate, then what will happen? The shear will take place. There will be deformation of this shaft. So generally the rule of the thumb is that you allow some kind of axial motion or flexibility for the transmission shaft so that it can elongate or compress depending on the temperature changes. Does it make sense, guys?
Yeah.
Yes.
Background noise here, but Let me know if you have any questions so far, guys. Any questions, guys?
Can you
From
go over that again, Professor?
Hi?
I have a question as well.
Yeah, go ahead.
Someone asked if you could go over it one more time, and then I have a question in relation to it as well.
Oh, so what I was basically saying that when you are mounting the bearings for the transmission shaft, you have to make sure that the bearings are arranged such that it allows the motion of the, it allows free movement of the transmission shaft in one direction. Because if somehow the bearings get stuck and it will not allow the movement of the shaft it will not allow the elongation of the shaft, then what will happen that it will seizure will take place. The bending or the transmission shaft will seize at its own place, and it will basically have permanent deformation and failure of the component. So here you are allowing the bearings to actually move in one direction. So that means if there is elongation happening, then the transmission shaft can elongate because of excessive temperatures in the machine or in the material in the assembly. Does it make sense?
Yes.
And what was the second question that you are having?
I was just confused by the explanation, but it makes sense now.
Okay, got it. Thanks. Okay, I believe the last part of this transmission shaft design consideration is the different types of pins and keys or torque transmission components, basically the how to connect two pieces together. So if you're mounting a gear, how will you ensure that transmission shaft and gears are basically connected together? So there are different components like keys and pins, set screws, splines that allows the movement of the gear or the pulley or the sprocket or any other component is mounted on the shaft to rotate along with it. So the transmission shaft is rotating at the same time. Any component that is mounted on this splines, for example, will also rotate at the same speed or the same direction. So you can have arrangement like keys. The keys are basically rectangular pieces of material that connects the inner material with the outside. The inner material is your transmission shaft. Outer material is basically for a gear or for a pulley, and they are connected together using this key, small piece of material that connects the two of the different components together. So if you are mounting a specific gear on a shaft, so there is a friction, for example, but you cannot rely on the friction for high speed application or high torque application, because if you're relying only on friction, which happens in case of set screws, you can use set screws to connect two pieces together. But then if there is no sufficient friction, then there will be related slippage happening. To prevent the slippage, you can use splines or you can use keys or pins. And generally, splines are generally used when you have very high torque, typically high torque transfers, and they are very expensive to manufacture than keys. Keys are generally the preferred choice to connect two pieces together, two parts together. And the reason being that keys are relatively inexpensive. And suppose you have a high torque application, then keys are the first that will fail. So keys will act like a fuse wire. So in case there is a high torque transmission happening, then what happens? The keys will fail. So it is just like a tipping point of fuse that will just snap stuff. And you can always replace the keys because keys are inexpensive to make and produce or fabricate. So that will help to prevent the failure of either the transmission shaft or the failure of the gear or the pulley that is mounted on it. So generally the keys are the preferred choices of connection points or torque transfer transmission components between a gear, a pulley, and the shaft. Splines are used as well, but splines are generally difficult to fabricate and manufacture and inexpensive as well. And they are generally used when you have very, very high torque transfer taking place. So those are some of the pros and cons of using a specific transmission components for torque, transmitting from transmission shaft to another component. Are you guys following it so far?
I have a question.
Yeah, go ahead.
When the key breaks, does the rotor keep spinning, but the gear doesn't spin anymore?
Yes.
Okay.
Yeah, so it is just like a fuse wire. So you have an overload and the fuse wire just tips off or basically snaps.